Now we want to talk a little bit about how refraction relates to the behavior of a lens. Okay, so let's start with the idea of a cylindrical lens. Now we could have water, there is water here. If we remove the label and clean off the cylindrical part of this bottle and run light through the bottle, it's going to be refracted. Okay, if we run beams of light in this direction through the bottle, it'll be refracted. Now let's take a look at what we see from above. If we're looking down on the cylindrical part of the bottle from above, we imagine a number of rays coming in parallel to the axis. So we got this central axis that goes through the center of the bottle. This central axis of the bottle, this central axis goes through the central axis of the bottle, and hopefully you understand what I mean by that. Let's take this ray right here. Well, when this ray meets the bottle, this ray is very small, and the part of the bottle that it encounters is essentially just a plane. So it's very much like this situation. We hit the bottle. There's a tangent plane here with which we interact in order to refract. The tangent plane is perpendicular to the normal line being a radial line from the center out to the point of intersection between the ray and the surface of the bottle. So we have our angle theta sub I between the ray and the normal. Then we have a refraction. The direction of the beam changes, and we have the refracted angle theta sub r. And theta sub I and theta sub r are related by Snell's law. The sine of theta sub I over the sine of theta sub r is equal to n2 over n1, or reciprocals of those two. Okay? Now, every beam, the beam here, well, it's going to be interacting with a tangent plane here. We have the normal, we have the incident and the refracted angles here, and here the central ray, of course, is going to hit at a perpendicular, so it's not going to be refracted. And these two, so we have this convergence, sort of a convergence of these rays, and they're going to hit the opposite side of the bottle. Then they're going to be refracted away from the normal a little bit, but they're eventually going to tend to meet at a point out here. Now, when I say tend to meet somewhere around a point out here, maybe on the central axis, I'm going to say that the beams near the axis will focus near one point, which we call the focal point. The beams that are far from the axis are not going to be as close to what we call this focal point. We'll define the focal point as being the point at which beams, okay, well, if we think of beams being closer and closer and closer, being confined, a bundle of beams being closer and closer and closer to the central axis, the closer they get to the central axis, the more closely they're going to bunch at one point, the more closely they're going to intersect, the smaller the region in which they will intersect out here. And in the limit, as these bundles approach the central axis, we're going to have a limiting point out here, and we would call that limiting point of intersection the focal point. Whether they understand all that or not, just, they're going to focus near some point out here. And we're not that interested yet in what happens with an actual cylindrical lens. I'll also mention that if it's water in this lens, these rays will intersect. A ray on this side of the axis will hit the back of the container on the same side of the central axis. If we have a high enough index of refraction, the beams could actually refract to where they cross the central axis before they get to the other side. The index of refraction has to be sort of high, but there are substances that have that sort of index of refraction. So the picture I've drawn here corresponds to indices of refraction less than about 2. In any case, over here, now we're going to talk about a thin lens. Okay, a thin lens, this is a thick lens. Okay, a thin lens is going to be much thinner. We have the parallel rays coming in again. there's a ray that hits at the center where the surface, I'm standing right in the way of what I'm talking about. We have these rays that come in here. They're parallel. There's a ray kind of in the center that hits the lens at a point where the tangent plane is perpendicular to the incoming ray. Okay? Now, the ray up here is going to be refracted more. The ray near the center is going to be refracted less. There is a little bit of offset between the direction of this beam here and let's say a bit of offset between the distance of the beam coming in relative to the central axis and where the beam comes out of the lens. It's going to be a little closer to the central axis. So the beam actually kind of jogs over a little bit here due to the way the internal reflection occurs, or the two refractions occur within the lens. For thin lens, that's going to be a small, there's going to be a small difference between this distance here and this distance here. Okay? Now, these rays all appear to be converging towards some point right about maybe here on the other side of this board. The beams then refract and converge at what we're going to call a focal point. Okay? For thin lens, the refraction and the convergence isn't perfect due to some of the factors that I mentioned and loud people in the hall. But you have with a good and a pretty thin lens, you're going to get pretty good convergence. So you're going to have pretty good convergence on a point out here, and the ideal point at which they converge is called the focal point. In both cases, the focal point is going to be regarded as the point at which initially parallel rays will be refracted in such a way that they converge. The focal point is the point at which initially parallel rays converge, here or here.